So the first question in the chat is, with critical numbers, are they only increasing and decreasing concave up and concave down? So critical numbers are x values in the domain of f, such that f prime is 0 or f prime is undefined. So critical numbers don't actually have anything to do with whether the function is concave up or concave down, because concavity depends on the second derivative, and critical numbers are only the first derivative.
Okay.
And they give us where the function might be changing from increasing to decreasing or vice versa, but not necessarily.
Can it also be with 2 ups or 2 downs?
Yes. So for
Okay.
example, this is my rendition of x cubed, f of x equals x cubed. And there would be a critical number right here because that is a horizontal tangent. So the first derivative would be 0, but this function is increasing on both sides. So it's not necessarily going to change from up to down or down to up at a critical number. Does that answer the critical numbers question?
There we go. Sorry, I was frozen, or you were frozen. Somebody was frozen.
Does that
Okay.
clarify the critical numbers?
Yeah, well, I just, because now if it was like a concave down and a concave down, so if it does like a hump,
Mm-hmm.
does that make it a critical number, or does it, yeah, like at the top, would that be considered a critical number?
It's
Yes.
a critical number because the first derivative is equal to 0 here.
Okay.
So it's a critical number.
Okay.
Okay, so the second question in the chat, how do you tell there's a hole in a graph by looking at it? You can't. We cannot, you can't graph a function and see holes because they are just infinitely small holes. When we're graphing by hand, we like intentionally put an open circle to show that there is a hole there. But if you're just graphing on Desmos or a graphing calculator, it's not going to show you holes. So we have to find holes through algebra.
Okay.
And so holes are places where the function is not defined, but that factor cancels.
Okay.
So for example, if we had, I'm just going to write this in factored form. If we had something like this, well, if we had something like this, since x minus 2 is a factor on both the top and the bottom, there would be a hole at 2.
Okay.
But since the x plus 9 factor would not cancel, this is going to be an asymptote.
At -9. Okay.
Yeah. And the last question in the chat, if you get a decimal from a square root. So basically, I think the question is, should you leave it in the simplified radical form, or is a decimal okay? And the answer is that it depends on the context of the problem. So the instructions say, I think, let me see if this is
Yeah.
that. Okay. No, I
just didn't know if it was just for answer or just for solving.
Okay, so if you get a radical at some point when you are solving, you should leave it in simplified radical form, because if you round it, then that's going to throw off the rest of what's happening.
Okay, yeah.
So don't round until the very end if it's appropriate to round at all.
Okay, gotcha.
So there's like money things, if you get a decimal, you should round to cents. If, like, for example, the very last question says round to the nearest book, so you would round to the nearest whole number, since we're talking about books.
Okay.
But if you get a decimal in the middle of a problem, we really shouldn't round, because it might mess up what comes after.
And with that answer, can we just put x equals, or should we label it with a per book? Or
you should use units.
Units, okay.
Yeah, so on word problems, application problems, include units in your answer.
Okay. Thank you.
Yeah. And in the chat, do you use Adobe Scan? Yes, so whatever scanning app that you usually use for your homework, you'll turn in the test just like you do your homework.
Madeline?
Yes.
I didn't put it in the chat, but I did have a question. I got here a little late.
Yes. Yeah. You can use the chat or not use the chat, either way.
Okay, awesome. And I think I'm lagging, or you're lagging. It's a little iffy.
You're muted.
Oh, I'm sorry.
Yeah, I think there might be a lag.
Okay, so I just had a question on step 2 of the graphing. When you're looking for your partition numbers, I was able to find the partition numbers. I do understand it, but I just had a question. When you set the bottom to 0, that makes sense, because usually it's like x to the third or x squared, x cubed, and that makes sense for it to be 0. But then when you set the top, in this case, going off the notes, we had -2x plus 16 over x cubed. Why did we still include the x cubed in that? And when it says just set top to 0, we still included the bottom part.
Do you happen to remember what day of class that was?
Yeah, it was the day we let's see. I have it written down on the step 1, but I don't know where step 1 is.
I think
3-9.
Yes. Okay.
Yeah.
Let me just make sure I know what we're talking about here. Okay, so this was the problem we're talking about: x squared plus 2x minus 8 over x squared. Oh, someone is frozen.
I think you said x cubed.
I thought so too, and now I'm confused.
Little lower. Oh, right.
Oh, there.
Yep, right. Right there. Okay, I guess you didn't set it there. I don't know why I had that set.
Yeah, because I just rewrote the derivative and it got kind of separated here. But yeah, f prime was this. And so I wrote it equal to 0. But really what that means is just we need to set the top to 0 and solve.
Okay, so either way, it's just the top. We're not going to be including the x cubed.
Right.
Okay.
If we're finding where the first derivative equals 0, we just need the top.
Okay, awesome. See, that little part where it cut off, I think that's all I was looking at, so it really threw me off last night.
Okay.
All right.
Yeah, sorry about
Awesome. Next page.
Any other questions? While you're thinking, there's just one thing I want to mention. On the graphing problem on 3F, it says these things that I just want to highlight. It says include all information found in the previous step and label every point. I don't know how to spell label. So in the previous steps, you found intercepts and you found extrema and you found inflection points. All of those should be like on the graph and labeled. So
Do you want them?
Sorry, go ahead.
Sorry, do you want them written down like in the bottom, like you did in the class session?
They should
Or
be
just on the graph is fine?
On the graph itself. So you don't necessarily need to like make notes again, because if you want to, that's fine. But they're all written on your previous parts. But what I mean is that if this is your graph, this is not what the graph looks like, by the way. Just making a random graph. Like, and that's actually not a good example at all, because that doesn't have any good points on it. If we have this, and we have this. This is a local extrema, so this should be labeled with whatever it is, and this should also be labeled. Since those are local extrema, and any inflection point, which would be something like this, that should also be labeled. I'm just making up random numbers here, but all I'm saying is that you should like put a little dot and like label the coordinates so I can see that you are taking your information from this first part and putting it onto the graph. And it also says to draw any asymptotes as well. So this would be the vertical asymptote on this graph, and this graph is more complex than the one on yours, but this would actually have sort of two horizontal asymptotes. But graph the asymptotes, label all of the points, make sure all of the information that you found in the previous parts is on your graph. And these intercepts would be on there too. Okay, what else?
Can we use completing the square on E for number 6? Or do you want us to plug it back in to the equation? I did both, but
E for number 6, you completing the square wouldn't be something you use.
okay.
That is just a plug-in.
Okay.
One other note that I want to make while you're deciding if you have any last minute questions is, where did it go? Here it is. Make sure that you sign the academic honesty contract. If you turn it in without signing that, I will have to hunt you down, which is not fun for me, so please don't do that. So even if you're handwriting this on a separate sheet of paper, you should still include that academic honesty statement and sign it. All right, any more questions? Last chance. Okay, so test 3 is due tonight at 11:59 p.m. Turning it in just like your homework. So today we're going to continue on in chapter 5 about integration. On homework 10, I posted the first part of homework 10 last week, which is not due until next Tuesday. And so that'll be these first parts of chapter 5 that we're covering last week and this week. Okay. So on Thursday, we started integration by substitution. So we're going to continue that today and then go on. So I just put those same formulas that we saw last week and that are in the book up here just as a reminder. So I'm not going to leave these up very long because we already have them, but these are sort of our 3 base formulas for integration. So these are on page 335. So our power rule, reverse power rule, our exponential rule, and our natural log, the 1/. So remember, u can either be the variable like x, or it can be its own function. So when it's its own function, that's what we're using it for substitution. And so I'm not going to leave this procedure up for very long because we went through these steps last time. But just as a reminder, these steps are also on page 335. So we are basically substituting everything in the original integral with things in terms of u, and then we're going to integrate the thing with the u, and then we'll go back to our original variable. And I just saw the question in the chat, are you going to give us these formulas on the test? No, I will not be giving you these formulas on the test. So these 3 are things that will be on the test. And this is the next test. Test 4 will be on chapters 5 and 6. And I won't provide these. But if you know the power rule of derivatives, we can always get to the reverse power rule for integrals and so on. Okay, so we're going to do some substitution practice. So here is our first integral for the day.
Looks like a chain rule.
Yes. So this is something that would have already had the chain rule applied to it, which is what substitution like undoes the chain rule. So now we are doing the integral. Which means we need to choose our u. So it's been 5 days and I know you've been working on the test.
Is it the inside part, the x to the 6 minus 2?
Exactly, yes. So our u is generally the interior part. So if we choose x to the 6 minus 2, that is probably a good choice of u, but we still need to check. And we check by finding the differential du.
That 6x to the 5th, u to the 3rd?
So the du is just the derivative of u, which is 6x to the 5th dx.
Oh, that's right. Okay.
So the du is just really just the derivative, but instead of having the dx under the du, it's over on the other side. So we choose this u, which looks like it's probably a good u, x to the 6 minus 2. And then we find our du to make sure they match. And so looking at this, we see we have u is this interior part. And du is that whole 6x to the 5th dx. So this u works because our u and du are going to be able to replace everything in that integral.
What happens to that 3rd power?
It stays. That is going to still be a part of what we are seeing because we're not going to be able to replace that exterior function with the u, but when we substitute our u, now we just have u to the 3rd du.
Oh, that's right.
So that u got plugged in for the whole x to the 6 minus 2, and the du got plugged in for the 6x to the 5th dx. So that exterior function, which is the 3rd power in this case, is staying there because that's the thing that we're actually integrating now.
Do we need to add the c or no?
We do, but we haven't actually done the integral yet. We've just substituted stuff.
Oh, that's right.
So now we have u to the 3rd, which we want to find the integral of. So this is where those rules come in. So I'm just going to go back for a second. So this is our first rule, which is it's labeled 4, 5, 6 in the book, which is why they're 4, 5, 6 here. So u to the n is the situation we have now. So that's where we use this reverse power rule, where we're raising the power by 1 and dividing by the new power.
So u4 divided by 4.
Right, exactly. And this is where we have the plus c, because we actually did the integral on that step.
So does the du basically replace the dx?
The du replaces the dx and the 6x to the 5th. Because
Okay.
here, when we found that differential du, we found it equals the whole 6x to the 5th dx.
Okay. It's coming back to me.
Mhm.
It has been a long 5 days.
Yeah, it feels like forever ago that we last had class.
And the du just falls off, right, at the last step? Well, not falls off, but goes away.
Yes, exactly. Because that was the like integral sign and the du are the sandwich that are putting the integral together. But once we actually evaluate the integral, that du is gone.
Okay, gotcha. Thank you.
And what would we use this for? What would it be useful towards, like in business?
So we will get there, but
Okay.
So we'll see an example in a bit about like if we know about the marginal profit, we can, or marginal cost or whatever, we can work backwards to find the original function. If we know marginal profit, we can find regular profit by going backwards. And in chapter 6, we will be focusing on
Word problems.
word problems, yeah. So we still have one more step here in this one though, because our original function or original integrand was in terms of x, but now we have a u, so we need to go back to the x, which just means plugging in that thing that we said was equal to u. And now we have our answer.
Where'd the
That's
x
not right.
squared
Yeah,
come
I don't
from?
know where that x squared came from. That should be a 6. Thank you.
Okay. I'm like, wait a second.
There we go. So our u is like that interior part. Our du is that differential, which is just the derivative, but the dx is over on the other side. We can substitute everything in terms of u, integrate that much simpler thing, and then go back to x. So far, all of our u substitution problems have been in this format where we have a power rule situation, but we have those exponential and logarithmic rules as well. So here is our next example.
Is that u to the -2 divided by -2?
So the power rule only works when we have our u in as
Oh,
the
that's right.
base and some number in the exponent. Here we have an x in the exponent. So when we have e to a power, just like in the chain rule, when we use the chain rule, if there was stuff in the power with the E, that was always our interior. And that's going to be true here also. So our
So
U,
negative 3x or
exactly,
negative 3u.
negative 3x. So u is always going to be a function with x in it. So we're replacing, like up here, we took that whole x to the 6th minus 2, which was our interior, and we said that's going to be called u now. So here we're taking that whole negative 3x, which is our interior, and we're calling that u.
Then our du will be e to the u.
So du, when we're doing du, when we're finding du, we don't look at the original at all. So du comes directly from u. So if u is negative 3x, what is du?
Negative 3
Negative 3, and then a little bit more,
dx.
dx, exactly.
Okay.
So finding du just means taking the derivative, really. And then there's a dx on the end.
Okay, that makes sense.
Okay, good. So then we can go back and look at our original integral. We'll bring that back. So this one, we're leveling up a little bit our substitution skills because there is something about this one that's a little different from the others, aside from that it's an E. And that is, as we're looking at substitutions, so u is our negative 3x, so that's going to plug right in there. The E is still our exterior, so the E is going to stay as it is. The thing
E
that
to the u.
it will be e to the u. But the thing that's different here is that we have just a dx. And in here, we got negative 3 dx. So we need to adjust our du equation so that we're replacing exactly what we have in the original, which is just a dx. Which
So add
means
3.
divide by negative 3. Or multiply by negative 1/3. So now we have a substitution that will substitute into exactly what we started with, which is just the dx. Up here, just contrasting, when we found du, that whole 6x to the 5th dx was exactly what was in the original, so we didn't have to make any adjustments. Here we had just that little extra minus 3, which was not in the original integral, so we can just divide both sides by that so that we have the dx only, which is what was in the original.
Mm.
So substituting, we have e to the u, so that u is going in for negative 3. In for the dx is that negative 1/3 du.
And is it multiplied?
They are multiplied. So we always have to make sure in substitution problems, we're substituting exactly only what we have in that original integral. So sometimes when we get a du, there's going to be an extra coefficient like this -3, and we just need to make whatever adjustment necessary so that we have our exact substitutions. This, as I wrote it, is a little awkward though, to have that -1/3 kind of squeezed in the middle. For integrals, as with derivatives, if we just have a constant multiple, like this -1/3, we can actually just put that on the outside of the integral so that it's out of the way. So our u was the interior, the whole exponent, -3x. We found du by taking the derivative, but then we just needed to make a little adjustment to that du equation to make sure that we had only what was in the original integral, which is just dx in this case. And then we were able to make the substitution. And anytime we have just a constant multiplied inside the integral, that can move to the outside. So that -1/3 is just going to multiply with whatever comes out of the integral. What is the integral of e to the u du?
E to the u plus c dx.
Just e to the u plus c. Yep, exactly. So e to the u is its own integral, just like it's its own derivative. But e to the u always is just itself, but we have to include that plus c. So that -1/3 is just multiplying with the e to the u, and the plus c is over off on its own. And then we can go back to our x. And if you prefer, we could also put that e to the -3x in the numerator.
I prefer neither.
Well, I do recommend leaving it as a fraction on this step, because if we go back, if you did -du/3 and put it as a fraction, it's harder to move that -1/3 out. So that's why I prefer it in fraction form rather than in dividing form. So we can clearly separate the constant and the du part. So we've done some with the power rule. We have seen an e, which we'll see another one in a little bit. So let's also do one with that natural log rule.
X squared minus 9?
Exactly, x squared minus 9. These ones can be a little tricky to see the interior part right away. But the clue is that when we're looking for u, its derivative should also be there, or at least a version of its derivative. So that little x on top is 1 degree less than x squared, which is indicating that that is a derivative situation. So if we choose u equals x squared minus 9, we should always check to make sure our du is also going to work. So du comes from u. U is x squared minus 9, so what is du?
2x dx.
Exactly. 2x dx. So when we look back at our original integral, we're seeing, okay, we have a u down here. And the remaining part of our integral is this little x on top and the dx on the side. And we have those two pieces in this du. So that's a good sign. Even though there's an extra 2 there, this is still good because it's the x and the dx are the important parts. So after choosing u and finding du, we should go back and look at the integral to make sure that everything has something to be substituted with. And then we just have to see if we need to make any adjustments to our du equation, and we do a little bit because that little, yeah, sorry, go ahead.
Does the 2 come out in front of the integral? Like we did with the negative 1/3?
It will, but we do need to do a little bit first before we plug back into the integral.
Oh, that's right.
Right now we have 2x dx on one side and we want only x dx because that's the stuff that's actually in the integral. So we actually have 1/2 du equals x dx. So now we have just the stuff that's in the integral equal to something with u in it. So u is in the denominator. The x is going to be a part of the du, so in the numerator we really just have the 1 left over. And I do recommend just putting that 1/2 on the outside. We can start with putting it on the inside and then pulling it out, but it's easier to just leave it out of the way. So that 1/2 du is what replaced our x dx, and then our little u replaced the whole x squared minus 9. So the substitution is all done. Everything from the original integral got substituted with stuff in terms of u. So I'm just going to write this little 1/2 out here, because that's just going to multiply with whatever comes out of the integral.
1 over x squared minus 9 plus c.
We haven't actually done the integral yet. So we're not ready to substitute back in. We need to find the integral of 1 over u du.
That's the natural
Natural log
Natural log, yes.
of u.
the absolute value of u.
Yes, exactly. Absolute value of u. So that is our third rule here. If we have 1 over u du, the integral is ln absolute value of u plus c. Oops. Sorry. And now we can go back and substitute our u in. Which was x squared minus 9. So the goal with substitution is always to simplify our integral so that it follows one of those 3 rules. Our reverse power rule, our e to the u rule, and our natural log rule. The thing about substitution is that the calculus step, there's only one calculus step, which is this one, and it follows one of those 3 rules. The tricky part of the substituting u is really just all algebra. Except I guess finding du is calculus also. But we've been doing derivatives a lot. So most of the tricky stuff here is just algebra, trying to piece together substitutions to make everything fit.
The order is what throws me off.
Yeah, so
Practice, practice, practice.
yes. So yeah, the order, it's kind of like there's basically 4 steps, and the first 2 steps are, or the second 2 steps are reverse order of the first 2, I guess. So we are doing the substitution, and then we're doing the integral, and then we're like undoing the substitution to get back to our original variable. I guess that was 3 steps that I just said.
I counted 6, so
Yeah, the way the book outlines it, it's 4 steps, but however many steps you want to help you remember everything, that works. So let's use this in an application problem. I'll give you a minute to go through this. Okay, so the marginal price. You just dropped something. Marginal price P prime at a supply level of X tubes per week for a certain brand of toothpaste is given by this function. So we have not talked about marginal price, but we've done marginal lots of other things. And so it's the same concept. So if we have some price supply equation, which means the relationship between the price that we're charging for an item and the number of items that we're making. The marginal price is just going to be the rate of change of the price per item that we're making. So marginal, whatever, always means the rate of change of that thing. So in this case, we know the marginal price equation, but our task is to find the price supply equation of the, if the supplier is willing to supply 100 tubes per week at a price of $3.65 each. So we're going to get to the 100 tubes per week part in a little bit. But first, let's focus on this first phrase. So find the price supply equation. So our goal is to find P of X. And note that this is a little p for price, not a big P for profit. So we know the marginal price.
So our U will be 0.01x.
Yes, and I'm just realizing that there is a typo in that marginal price equation. There's an extra U down, or an extra 0 in front of the E. Those two numbers should match each other. I'm sorry about that. So yes, so if we are going from a derivative to an original function, that always means that we are going to take the integral. So we did this with a cost function last week. And now we're doing it with, or a marginal cost function last week, and now we're doing it with a marginal price. So yes, our U is that exponent part.
And our DU is 0.01e. dx.
So we don't look at the original
Oh,
when we're doing the DU.
oh, there we go. Okay.
So du is just the derivative of u with that dx on the end. And so in this case, we do have, so we have our u, which is that exponent part, and we have our du, which is the 0.01 dx. So in this case, we don't actually have any adjustments to make to our du equation because the exact du, 0.01 dx, is in our original integral. So when we do our substitution, the u is going in for the 0.01x in the exponent, and that whole 0.01 dx is being replaced by du. So we substituted all of our stuff with things in terms of u, and now we can do the integral. What's the integral of e to the u?
E to the U plus C.
Yes, exactly. E to the u plus c. So if we put our u back into that function, we now have e to the 0.01x plus c. And that is almost our price equation. So when we do the integral of p prime, we do get p. However, there's still a little bit of uncertainty around this c.
I'll plug in 3.65 or 100.
We need both.
Hmm.
Let me make a little extra room here. So we were told that this supplier is willing to supply 100 tubes per week at a price of $3.65 each.
So divide 100 by 365 to get individual cost.
So C here is just our constant that's added to the end of this function. It's not cost.
Oh, that's right.
But we have this equation. We have the price on the left side. We have the units being produced up here in the exponent x, and we need to know C.
Multiply.
This is an ordered pair, basically. It's an XY pair, but our Y
Oh.
is P. So this statement is saying that when the price is $3.65, we're going to be producing 100 tubes of toothpaste, and we can figure out C based on that. So we're being given conditions that allow us to make an equation where C is the only variable, and now we can solve for C. It's going to bring up Desmos.
That's 1 e to the 1.
Yes, I'm just going to put it all in together. So we have 365 minus E
All right.
to the 0.01 times 100, which would be 1. Whoops. And we get 0.9317, and E is irrational, since this is never going to be an exact number. So I'm just going to round this to 2 decimal places, since our price is in 2 decimal places. So 0.93. So our price function, which we were actually looking for, is the e to the 0.01x, which is what we got from the integral, plus the c, which we just found. So anytime we want to find an exact function, starting with its derivative and doing the integral to go back to the original function, we need a little bit more information in order to figure out what c is. Last week, we saw one where we were given the fixed cost. So it told us that we had a marginal cost function and we did the integral to find the original cost function, and it told us what the fixed cost would be. So we were able to find c that way. Here, we're being told this ordered pair of p and x and p, that we can plug in to figure out what c is. So there should always be some way to find c if we're looking for an exact function. So let's just do part B just to see that c in action again. Here we go. Okay, so here we have the same question. How many tubes? Oh wait, no, sorry, I was reading the question wrong. This is not a C in action question. So how many tubes would the supplier be willing to supply at a price of $3.98 per week? So we have our function that we found. So first of all, which variable are we going to be solving for here, p or x? If we want to know how many tubes the supplier will sell.
X.
Exactly. So x is our supply. That's how many tubes the supplier is going to give us. So we're being told that we have this price of $3.98. So we can just plug that right in. So this question is not a calculus question. This is an algebra question to use the function we just found. So just as a quick little algebra review, we need to get the 93 on the other side, so we'll have 305 equals e to the 0.01x. If x is in the exponent like this, what do we do to get it out of the exponent?
Square root.
No, square root can only undo
Oh.
a square.
Fraction. Divide, right?
No.
That just puts it in the bottom.
Hmm.
Just erase it.
I've seen that happen before, but it does not work.
It just disappeared. I don't remember.
Logs and exponents are inverses. So if we have an e on the bottom here, we can take the natural log of both sides. And ln and e have the same base, so they just cancel each other out. And then x is going to equal ln 3.05 divided by 0.01. Anytime we have our variable in the exponent and we need to solve to get it, we need to solve for that variable, we have to use a log to get it out. And so here our base is e, so natural log is a good choice because those two have the same base and they completely cancel each other. And so we had ln of 305 divided by 0.01, and we get 111.5, which, since we're talking about tubes of toothpaste, we'll just round to the nearest whole number, so 112. So this is not something that comes out in this class a whole lot, but it is an algebra skill that we need to have ready to go in times like this. Okay, so this is the end of section 5.2. So 5.1, we started using these three integration rules, but just for things that had x's. So it was x to the n, e to the x, 1 over x. Then in 5.2, we introduced substitution, in which is when we can have any kind of function in those three positions. That is the most complex integration we're going to have to do in this class, is the substitution method. We're still going to be doing more integration and applying it to things and looking at it in different ways, but we aren't going to have a whole lot of complicated integral methods here. So we are going to be doing some integration using technology also, which will be in either Desmos or a graphing calculator as well. But, but we're going to sort of switch gears before we start doing that kind of thing. There's one more layer of integration, which is not more complex, but has a little bit more, slightly more work to it. So if you'll remember, these, what we've been doing, have been indefinite integrals, which means our answer is always some function with this plus c. But there's also something called a definite integral. Oh, by the way, we're skipping section 5.3. Not because it's not important, it's just not specifically part of what we have to do for business calculus. So, which, if you didn't like seeing natural logs and e's in the previous problem, you'll probably be happy about skipping 5.3. Okay, so definite integral. We're gonna go through 5.4 relatively quickly because this is what's most important about 5.4 is the concept. And this is a different way of looking at integrals. So I am going to adjust this so we can see everything. I feel like my screen is kind of choppy today.
The intervals or integrals?
So this is integral, the definite integral. This word is integral.
Okay.
So yeah. So the definite integral, before I say what exactly that is, this is our question that we are going to think about for a second. So we want to know what the area between the curve and the x-axis is on the interval from x equals 1 to x equals 4. So that would be from 1 to 4. And we're looking for the area between this curve that's drawn and the x-axis. So this is a parabola that's drawn, a part of a parabola, so it's curvy. If this were a straight line, we would have a geometric formula that we could use that would be a trapezoid, so we could just do some measurements and plug stuff in. But here we have a curve, so we don't have any like exact geometry formulas to find the area of a weird, like almost trapezoid with a curvy top. So there's a mathematician named Riemann who came up with some ideas of how to approximate the area under here. So even though maybe we wouldn't be able to like geometrically calculate the area here, we could, I'm going to erase part of what I've drawn so it's not so messy. We could instead use shapes that we do know how to calculate the area of to make an approximation. So maybe I'm just going to divide this area up into 3 sections, and I'm just going to draw some rectangles that look like roughly the same height as the area under this curve. So if we calculated the area of those 3 rectangles, which we could do because area is just length times width for a rectangle, we could get an approximation of this area. It wouldn't be that great because we can see there's a bunch of extra stuff like going over the edge, and we're also missing these little bits here, but it would be like a not terrible guess. If we wanted to get a better approximation, we could just make more rectangles. So instead of making 3 rectangles, maybe I would try 6 rectangles. So I could make some a slightly better approximation by fitting 6 rectangles into this, around this curve. And now it's still not exact, but there's going to be less of these mismatchy edges. And so if we make more and more rectangles, the closer our approximation is going to be. So more rectangles means better approximation. you're not going to have to find the area this way. I'm not going to have you calculate these sums of rectangle areas. But conceptually, this is really important. So I am going to bring up a page on Desmos, which is a better visualization than me trying to draw smaller and smaller rectangles. So this is the curve that we were just looking at. It's blue instead of red now, but it's that same function. And here we don't have the dividing lines between the rectangles, but we can see there's a rectangle down here, there's a rectangle down here. And so we can sort of fit these rectangles under this curve. And where did it go? Oh, I scrolled down too far, that's why. So,
do you make these ahead of time, or are these already like available somewhere?
This one was available. I'm going to bring up another one that I made, but I'm also going to post the links to these so that you can play with them on your own time if you're interested.
Where are you posting them?
I will post them in Canvas. I'll post them in today's module and possibly somewhere else also so that it's handy after today. But I'll let you know where I post them.
Thank you.
So this one, so we have this function 1/2 x squared, and we have two endpoints 1 and 4, which were the intervals we were looking for. This bit we can just change whether the rectangles are hitting at their midpoint or whether they're hitting on their left side or on their right side. I'm just going to leave it on the midpoint for now. So here right now we have 5 rectangles, but if as I increase the number of rectangles, we can see the approximation is getting better. There's less going over and going under around the curve. So as we get more rectangles, so when we get 100 rectangles, we can barely even tell that it's not exactly the curve. So if we only have 1 rectangle, that's really a bad approximation. But when we have more rectangles, we get a better approximation. So these are called Riemann sums because we're adding up the sum of the areas of each of these rectangles, and Riemann came up with this idea. But of course, we have modern calculus. Well, this is actually early days calculus, but this sum that's written here on this left side, so value of the Riemann sum, this is the sum notation of what we're looking at here, which you're not going to have to use the sum notation, but this is basically saying the function itself gives the height of the rectangle, and W is the fixed width. So in a Riemann sum, every rectangle has the same width. And so we're taking the height times the width of each of these rectangles and adding them all together over the sum. And that sum gives us an approximation of the area. Now this is a little bit of a spoiler because we can see the integral here, but the actual area is 10.5. So as we increase, let me see if I can zoom out of here to show these. Okay, so as we increase the n and get more and more rectangles, our area approximation is closer to our actual area. If we only have 1 rectangle, it's pretty far off. So having lots and lots of rectangles is great, but we don't necessarily want an approximation of of the area, we want the actual area, and that is where integrals come in. I'm going to go back to our notes for just a second. I'm going to write a really informal version of the Riemann sum. Which is the sum of the height of the rectangle times the width over however many rectangles there are. And so really what that means is that we're going to have f of x times the change in x. So our width of a rectangle, I'm just calling delta x for now, which is the change in x, however much we're changing each width of a rectangle. And our height is the value of the function on that rectangle. So f of x here, if we have our width is here, delta x, the height of the function, whatever the function value is there, is the height, is the length of the rectangle. And we are saying this is going from n equals 1, or not n. I'll just say from 1 to n. So if we have n rectangles, we are adding up each of these different rectangles. They all have the same width, but their height depends on the value of the function there. It's going from 0 up to f of x, whatever our x happens to be there. And we're adding up n rectangles. This is a very informal way of writing this, but I'm just trying to simplify it into length times width with n rectangles added together. And so our calculus comes in with the limit because we know that we're going to get the best approximation when we have more rectangles. So if there are n rectangles in this interval to find the area, if we look at the limit when we have infinity rectangles, we are going to get an exact area so A to B is the interval that we're looking at. In this case, it's 1 to 4. F of x is still the height of these rectangles. And now dx is the width. So the analogs here are f of x is still the height. But now instead of having some substantive change in x, our change in x is dx. So this is an infinitely small width. So this is technically a width of 0. So when we take the limit as these rectangles, as we get infinitely many rectangles, all of the rectangles are getting thinner and thinner and thinner and thinner and thinner until really what's happening is that instead of adding together a bunch of rectangles, we're adding together infinitely many line segments that have no width, but when we add all of them up, we actually get a value. And so if we can imagine on this, if we were able to keep this slider going off to infinity, the number of rectangles we have would go to infinity and our area would turn into the integral. And this is a definite integral because we have endpoints now. We're going from one place to another. So all of that is not something that you are going to have to like do. I'm not going to have you calculate Riemann sums, but conceptually this is super crazy and super cool that we can take all of these rectangles and just make them super thin and have more and more and more and more rectangles. And now this concept of adding together rectangles turns into adding together infinitely many line segments, and we actually get to the area under that curve. So the moment we've been waiting for is the actual definition of a definite integral. Is this. I'm just going to give you a moment with that before talking about it more. This should say of. So the definite integral of f on the interval AB is this. So everything here is the same as it has been before. We still have the integral sign, we still have our function in the middle, and we have our dx. So we still have that same sandwich. The only thing that's different on this notation from our indefinite integrals is that we have an interval from A to B. So in this case, if we were calculating the integral here, our A would be 1 and our B would be 4. So we have a starting point and an ending point. So the second part of this is that geometrically, the definite integral is the cumulative signed area between the function f and the x-axis on the interval A to B. So we're going to look at some examples of what the cumulative signed part means. But basically, if we have a curve and we look at the area between the curve and the x-axis with whatever endpoints we have, that is what the definite integral tells us. It's telling us that whole area underneath the curve or between the curve and the x-axis. So I'm going to bring up one more Desmos thing so that we can talk about what this cumulative signed part means. Okay, so this is actually the same function that we were just looking at, 1/2 x squared. And so up here I have the integral from A to B of f of x dx. and Desmos calculates that for us. So we have 10.5 in this case. So this is saying geometrically that all of this green stuff, the area of that section is 10.5 units squared. So if we were able to measure this area, it would come out to 10.5. So if I bring B a little bit closer, maybe down to 3, we can see now the area is 4.33. So that's a smaller shaded region, so the area is smaller. That makes sense. If I slide A down to -1 maybe, or close to it, now we have this whole area together is our integral. So all of this shaded region from -1 up to 3 gives us the 4.66666.
What could that area represent?
Like in a real world sense?
Yes.
So the first application that we're going to do with this area is the Gini index, which is the index of income inequality in a country, which relates to different functions with each other to find the area between them, functions that relate the income inequality or equality of a certain country. The area also, the integral in the area sense doesn't always translate exactly to area in an application. So for example, one of our applications is going to be a consumer surplus or a producer surplus, which tells if a producer is able to sell products for a lower price, or excuse me, for a higher price than they expected, then they're going to get more money. But that is going to be when we start looking at the areas with more than one curve together and looking at the area between two curves rather than just the area between the curve and the x-axis. But this area is often not specifically area, but it'll represent something else. It's area on a graph that we're looking at, but it can be extrapolated to represent something else in applications, which we will get into. It's also, I am getting excited about integrals right now. In like higher level calculus classes, when we're doing multiple dimension type of things, integrals can be found to find the like the volume of weird shapes or the mass density or the density at certain points in a certain thing. So if we're making a part for an airplane and we need to know the center of mass for that part, then integrals can do that for us. So there's all sorts of applications for integrals, whether it's geometric like the specific area or like something that doesn't actually turn out to be a geometric application.
I see. Thank you.
You're welcome. No, that was exactly what we wanted. But yeah, so integrals are great. They do all sorts of things, and we will see more things. So for now, right now we are seeing this area between this curve and the x-axis as the physical representation of our integral. This particular curve never goes below the x-axis. So I am going to change this so that now it is partially below the x-axis. I'm just going to change that. So now same type of thing, but part of it dips below the x-axis. And we'll notice that if I change this signed area so that it's only in that bottom part, or change the area, the shaded region, so it's only in the bottom part, our area is now negative, or integral is now negative. So in that definition of definite integral, when it says the definite integral is the cumulative signed area, the signed part means that above the x-axis, let me put this in parentheses. So the signed part means the area above the x-axis is positive and area below the x-axis is negative. So in that way, it doesn't translate exactly to our geometric concept of area, because area generally we think of as positive, but here it's negative because we're integrating the function value. So if the function value is negative, then the height of the rectangle would also be negative. So the cumulative part means that we're adding up any separate areas. So if I move this over, I can actually get an area, can get an area close to 0. So if the negative part and the positive part are almost the same, they're just about going to cancel each other out, and they do totally cancel each other out in some functions. So the cumulative part means that if we have more than one shaded region, if we're going below the x-axis and above the x-axis, the positive part and the negative part add together to make our value of our integral. So I am going to post the links to these two things that I've shown today, just so you can sort of see how those integrals work, which is going to be optional but fun, in my opinion. And you can change this function to, I'm going to bring up a function that we don't talk about in this class, but if you've ever done trig, this is a sine function, so it just goes up and down forever. And so if I put a on 0 and b on 2 pi, this area, or this integral, is 0 because the area above the x-axis and the area below the x-axis are exactly the same, so they're totally canceling each other out. So that can happen as well. We haven't seen how to actually calculate the definite integral yet, which we will do on Thursday. So here we're just sort of relying on Desmos to tell us what that area between the curve and the x-axis is, but on Thursday we will actually be calculating these definite integrals by hand. And so we have, in these last few minutes, we have one example to just sort of see how this is working. So here is a graph of a function, and I've labeled these 4 parts A, B, C, and D. So we have A and C below the x-axis and B and D above. And then we have all of these, the little lowercase letters are the x values. So A to B is, or A is here, B is here, C, D, F. So we have the areas of each of those sections. If we're talking about area in a strict sense, all of them are written as positives. And we want to calculate some integrals. So this is practice in understanding the relationship between the integral, the definite integral, and what we're seeing on the graph. And that curve is f of x. So if we want to find the integral from b to c, so b is our starting point, c is our ending point, of f of x dx. That means we're starting here at b and we're going over to c. So this is a definite integral, which means graphically it's the area between the curve and the x-axis on that interval. So here, what the area that we're looking at is this area capital B, which means that our integral would be 21.33.
And that's it?
That's it for this one. Yep.
Nice.
They'll get harder in 5.5. So that one is like our warm up. Number 2, now we want to know the integral from c to d. So starting at c and going up to d.
22.05.
Almost. So that shaded region has an area of 22.05. So what is the integral? There's just a little bit more to it.
Negative 22.05.
Exactly. So it's just negative.
Okay.
So the integral just takes into account if it's above the x-axis, it's positive. If it's below, it's negative. Otherwise, it's just that same exact measure of area. So number 3, we are integrating from c to f now. So now we have this whole part. So now there are 2 sections that we need to pay attention to.
So would it be a negative 22.05 plus 3.09?
Exactly. And whatever that turns out to be. So that's the key here. So if we're finding an integral, a definite integral over some interval, geometrically or graphically, it is that signed area all added up. Areas below the, or excuse me, above the x-axis are positive and below are negative. And so I'm going to leave number 4 as a little cliffhanger for Thursday, just to review what we just did before we go on to actually calculating these by hand. And so that is all. I will see you on Thursday.
Thank you, Madeline. Have a great day.
You too.
Thanks. Bye-bye. No in-class assignment because I got too excited about integrals and forgot.
I mean, they are pretty cool, so
Yeah, they
it's
are.
understandable.